All right, this video is going to go over Module 2 Homework 5 notes, talking about exponents and scientific notation. Exponents are helpful because they allow us to write repeated factors in a more condensed form. So instead of doing x times x times x, we could just write it as x cubed. So an exponential expression is the base plus the exponent. So we'll come back to that in a second. A coefficient is the number in front of the exponential term, so not raised to a power. The base is the number that's being repeated, and the exponent is the number of times that base is being repeated. So our examples say identify the coefficient, the base, the exponent, and the exponential expression, and then evaluate. So in this case, we have 2x to the 10th power. So if I were to write this out, we have 2x to the 10th power. So that 10 is only applied to whatever is directly underneath it. So it is only applied to the x. So I just have 1, 2, and I have 10 x's. So if I were to write it out, that would be what it would look like. 2 times x times x times x all the way 10 times. So that coefficient is the number out front that is not raised to a power being repeated. So in this case, that is going to be our 2. So our coefficient is 2. Our base is the number that's being repeated. So in this case, our x's are being repeated. So our base is going to be x. And our exponent is that number of times that it's being repeated. So our exponent is going to be 10. All right, next example, 5 squared. So if we were to write this out, this would be 5 2 times, so 5 times 5. So for our coefficient for this problem, there's not a number that is out front. But I could say, all right, 1 times 5 is still the same thing as just 5 times 5. So in this case, there's not a distinct coefficient, but we can always say that it's 1. 1 could be outside. So our base is the number that's being repeated, which in this case is going to be 5. And our exponent is the number of times it's being repeated. So in this case, our exponent is going to be 2. So next we have -5 to the 4th power, just like we talked about in this first example. So that 4 is only applied to whatever's directly underneath it. So it's only applied to the 5 in this case, not the negative. Be very careful. So that negative is out front. That negative is just saying a -1. So I can have a -1 out front, and then I have 5 to the 4th power, or 5 repeated 4 times. So 5 times 5 times 5 times 5. So here we can see that our coefficient is the number out front, which is going to be -1. Our base is the number that's being repeated, which is 5. And our exponent will be 4. Next example, -5 to the 4th power. So in this case, the -5 is in parentheses, so it's grouping the negative and the 5 together as one term. So that whole thing is being repeated 4 times. So it's really like -5 times -5 times -5 times -5. So again, there's no number out front, there's no coefficient. So we can always write a 1 there. So in this case, our coefficient is going to be +1. Our base this time is the number that's being repeated, which in this case is -5. And our exponent will be 4. So our calculator knows this rule and knows this thing. So whenever you're putting this into your calculator, make sure that if you want the negative repeated, that you put it in parentheses. If you do not want the negative repeated, you do not put it in parentheses. So for example, going to our calculator. So here I have our example was, the first one was negative, so down here is our -5 to the power, so here's my caret, my power button, to the 4th power. So -5 to the 4th power. So pressing enter. So that's saying -625. Oops, sorry. -625. So if I were to put it in parentheses, so clearing this out, in parentheses, -5 to the 4th power, it's going to give us positive 625. So going back to our notes, that makes sense because here we have only one negative, so that's going to make this negative 625. Down here I have 1, 2, 3, 4 negatives. So the 4 negatives will cancel each other out, and that will give us positive 625. So make sure you realize that in your on your calculator. So dealing with exponential expressions, let's start to do operations. So let's start with multiplying. So multiplying exponential expressions. If we have 5 squared times 5 cubed, we have a little shortcut for this, but let's see why this happens. So 5 squared will give, x squared times x cubed. So x squared will be x times x times x cubed. So x times x times x. So total, I have 1, 2, 3, 4, 5 x's. So I really have x to the 5th power. So what did we do behind the scenes to get x to the 5th power so that we don't have to write it out every single time? Well, we added the exponents. So x to the 2nd power plus 3rd power. So 2 plus 3 will give us x to the 5th power. So whenever we're multiplying, notice they have the same base. They're both x's, so they're like terms. We are going to add our exponents. So to multiply exponential terms, we're going to multiply the coefficient as we normally would do, so any numbers out front. And then just like combining like terms, we're going to keep the base the same and add our exponents. So again, you can only combine like terms that have the same the same base. So let's do an example. Simplifying x to the 5th, y to the 6th, times x cubed, y to the 8th. Again, combining like terms. So let's combine our x's together. And then we'll combine our y's together. So starting off with our x's, we are multiplying. So we know we can add our exponents. So x to the 5 plus 3 power. And for our y's, we have y to the 6 times y to the 8th. So adding those exponents, we get 6 plus 8. So simplifying, we would get x to the 5 plus 3 is 8. Y to the 6 plus 8, which is 14. We combine all of our like terms, so that is our final answer, x to the 8th, y to the 14th power. Next example, it says to simplify negative 3x to the 7th times negative 3x to the 5th. Now, there's nothing outside of this first set of parentheses or the second set of parentheses to distribute. So the parentheses in this case are just kind of grouping them together, kind of making it more organized, but it's all still multiplying. So we still have negative 3 times x to the 7th times 3 times x to the 5th. So let's combine like terms here. So we have negative 3 times 3. Those are coefficients, just numbers out front. Negative 3 times positive 3 will give us negative 9. Now combining our x's, x to the 7th power times x to the 5th power. So we have x, we're multiplying, so we can add our exponents. So 7 plus 5 will give us negative 9x to the 12th power as our final answer. One more example for multiplying. So we have 2 to the 4th power times 2 cubed. So if you notice, I have, they're both base 2. So again, we're going to keep our base the same and add our exponents. So 2 to the 4 plus 3 power, which will give us 2 to the 7th power as our final answer. So notice these 2's are bases. So really, I just have a bunch of 2's. If I were to write this out, I have 2 times 2 times 2 times 2. That's our 2 to the 4th, times 2 times 2 times 2, which is 2 cubed. So notice now I just have 2's. So now I have 7 2's total. But they're still 2's. Everyone always wants to multiply it and make it 4 to the 7th power, but we still just have now more 2's. We have 7 2's total, but make sure you keep them as 2's. So keep our base the same. Just like up here, we kept x the same and we just added our exponents. So that's multiplying. Now let's get into dividing. So same concept. Let's now divide our exponents. So we have 2 to the ninth times 2 squared. 2 to the ninth divided by 2 squared. So let's do it long way first. Let's write it out. So that way, if you like writing it out better, a lot of visual people like to write it out instead of having to memorize little shortcuts. Go for it, whatever works best for you. So up top, I have 9x's. Divided by, on the bottom, I have 2x's. So if you notice, x divided by x is just a fancy way of writing 1, so those can cancel out. Same thing, x divided by x is a fancy way of writing 1, so those can cancel out. So I'm left with 1, 2, 3, 4, 5, 6, 7 x's. So x to the 7th power is our final answer. So if you notice here, what we did was we subtracted our exponents. So we're going to divide the coefficients, the numbers out front like we normally would do, keep the base the same, subtract the exponents. Now we're going to talk about, notice that this is 7x's at the top. So that means positive 7 because it's at the top. On the bottom, there's nothing left over underneath. So I don't need to write that fraction bar anymore because there's nothing on the bottom. It would be the same thing as saying over 1. Which we usually don't write, a number over 1. So, but we have this problem. What if it was flipped? So what if, for example, let me get a different color so we can do a little example here. What if we had, for example, the other way around? If we had x squared divided by x to the ninth, we would have 2x's up top and then 9x's on the bottom. So that means those would cancel out. What's left over up top? Well, nothing besides these 1, so it's going to be 1 up top. And on the bottom, we have 1, 2, 3, 4, 5, 6, 7 x's, so x to the 7th power. So if we did our little subtraction shortcut here, we would have x squared, x to the 2nd power minus the 9th power, which would give us x to the negative 7. So because that negative 7 is there, it's telling us that those x's are going to be left over on the bottom, on the denominator. So this is what this is saying. We're still going to do top times bottom, numerator minus denominator. So in this case, 2 minus 9. If the exponent is positive, then it's going to go to the top, the numerator. If it's negative, it's going to go to the bottom, to the denominator. So keep that in mind. So let's do an example to kind of show us this. So simplify 12x to the 10th, z to the 8th, all over 14x to the 8th, z to the 7th. So again, we are going to combine like terms. So starting off with the 12 divided by 14. So let's see, I can simplify that. They both have a 2 in common. So I can factor or divide out a 2 from the top and the bottom. And we're left over with 12 divided by 2 is 6, 14 divided by 2 is 7. So 6 is left over up top, 7 is left over on the bottom. There's nothing that 6 and 7 have in common, so I cannot simplify that farther. So now let's do the x's. So x to the 10th divided by x to the 8th. So let's write that out. We know we are going to subtract our exponents. So x to the 10 minus 8, notice it automatically goes to the top. If it's negative, we'll deal with that later and then flip it to the bottom. And then last but not least, we have our z's. So z to the 8th over z to the 7th. So we have our z's, and then we have 8 minus 7. So 6 is going to stay up top, 7 is going to stay on the bottom. X to the 10 minus 8, which is 2. Z to the 8 minus 7, which is 1. So that's really just 6x squared z up top. I don't need to write that first power. It's just automatically know there's 1 z all over 7 as our final answer. 6x squared z all over 7. All right, so our next example, z to the 7th divided by z to the 7th. So if we were to use our little shortcut, 7 minus 7 would give us z to the 0 power. That means no z's are left over. So what would we have there? Z to the 0 power, anything to the 0 power is always going to be 1. Let's talk about why really quick. If we had 7 z's up top, 7 z's on the bottom. If we were to cancel, z divided by z goes to 1. 1, 1, 1, 1, 1, 1. All of our z's canceled out. All we're left with are all of these 1s. Well, 1 times 1 times 1 times 1 times 1 times 1 times 1 is still just 1. So whenever there's nothing there, it cancels out to 1. That is what's called our zero exponent property. Any non-zero base raised to the 0 power is 1. So anything to the 0 power is going to be 1. So for example, 3 to the 0 power, 1. X to the 0 power, 1. Those are my favorite. So that's the zero exponent property. So we kind of dealt with negatives a little bit, but just again to reiterate. So for example, negative exponents, a to the negative n power means I have 1 over a to the n. So that negative exponent means it's going to flip down to the bottom. Well, what if I have a negative in the bottom? So 1 over a to the negative n power. We cannot have a negative exponent. So basically what that negative does, it flips it. So if it's up top, it's going to flip it to the bottom. If it's on the bottom, it's going to flip it to the top. When writing negative exponents, they move across the division line or across the fraction bar to become positive. We have to write our answer using only positive exponents. So when exponents move across the division line or the fraction line, they change signs. So if it's a negative exponent on the top, it's going to move to the bottom to make it positive. And likewise, if the negative exponent is on the denominator on the bottom, we're going to move it to the top to the numerator to make it positive. And we'll see some examples of that in 1 second. But before we do that, let's deal with parentheses. So what if we have a power to another power? So a power to another power. Or an exponent to another exponent. I don't like the way this looks. Power to another power. So what if we have x squared cubed? Well, let's think about this. X squared cubed means I have x squared 3 times. So x squared times x squared times x squared. Well, x squared is x times x times x times x times x times x. So that will give us 1, 2, 3, 4, 5, 6 x's total. So x to the 6th power. So here, whenever we have a power to a power, with these parentheses here, we are going to multiply our exponents. So double exponent, an exponent raised to another exponent, keep the base the same, and we're going to multiply our exponents. So for example, a to the x power to the y power is really just a to the power of x times y. For example, 3 squared to the 4th power. We have a power to a power, so we are going to multiply our exponents. So 3 to the power 2 times 4, which is 3 to the 8th. We can just leave this just as 3 to the 8th because we like exponents, we use them. So instead of writing a really big number, we could just leave it as 3 to the 8th. Now that looks very similar to 3 squared times 3 to the 4th. Here we don't have a power to a power. These are two separate things that are being multiplied. So this time, going back to our multiplying, we are going to add our exponents. So up here, we had a power to a power, so we multiplied. We only had one base. Here we have two separate terms. So two totally separate bases, two separate things. We're combining like terms by adding the exponents. So we would get 3 to the power of 2 plus 4, which would give us 3 to the 6th. 3 to the 6th. Next, we have 3x squared. So we have 3x 2 times. So we have 3x times 3x, which is really just 3 times x times 3 times x. I like to write it out kind of separately like that because it helps me see that, okay, we have 3 times 3, which is going to give us 9. And then we have x times x, which is going to give us x squared. So 9x squared will be that final answer. Last but not least, we have 3 plus x squared. So again, we have 3 plus x 2 times. So this is what's called a binomial, meaning we have two terms. I have 3 plus x and then 3 plus x. So here it's super important. We have to distribute. So 3 times 3, which will give us 9. 3 times x, which will give us a positive 3x. So notice my 3 went to both terms over here. I distributed my 3 to both terms. Now same thing with the x, distribute x to both terms. So x times 3 will give us another positive 3x. And last but not least, x times x, which will give us a positive x squared. Lastly, I can combine like terms. I have 9. 3x plus 3x, which will give us 6x, so plus 6x plus x squared, and that'll be our final answer, 9 plus 6x plus x squared. All right, so kind of putting this all together. So simplifying and writing our answers only using positive exponents. So we have negative 3x squared y to the negative 3 power, all to the 4th power. So that means I have 4 of these things. So instead of writing out, I could write out 4 of these things, but I know that I'm going to have negative 3 4 times. I'm going to have x squared 4 times, and I'm going to have y to the negative 3rd power 4 times. So because there was no adding or subtracting here, I knew I didn't have to distribute like we did up here. We just knew there was going to be 4 of them. So technically, we just distributed the exponent to each term. So negative 3 to the 4th power. So I can plug this into my calculator. So turning it on. In parentheses, exactly like it says, negative 3, closing my parentheses, using my caret for my exponent to the 4th power, will give us 81, positive 81. X squared to the 4th power. So here I have a power to a power. So we are going to multiply our exponents. So we have x to the 2 times 4 and y to the negative 3 times 4, which will give us our final answer, or not our final answer, but it'll give us 81. X to the 2 times 4 is 8. Y to the negative 3 times 4 is negative 12. Now, we have everything combined, but why is this not our final answer? I have a negative exponent. I have to write that as a positive exponent. So we said that negative exponents flip our term across the fraction bar. So that's meaning this y to the negative 12th is going to go to the bottom of our fraction. So 81's staying the same, x to the 8th is staying the same. They're up top, they're going to stay up top. But now that y to the negative 12th is going to flip to the bottom of our fraction to make it positive, y to the positive 12th power. And that will be our final answer, 81x to the 8th all over y to the 12th. So next example, x to the negative 6, y to the negative 6th all over a to the negative 3rd, all to the negative 5th power. So again, all of these terms are being raised to the negative 5th power. So again, I can distribute exponent to exponent and say they're all going to be occurring negative 5 times, so to speak. So x to the negative 6th to the negative 5th power. Let me rewrite this. X to the negative 6th to the negative 5th power, y to the negative 6th to the negative 5th power. That's exactly what I didn't want to happen. Let's do this. Okay. So x to the negative 6th to the negative 5th power, y to the negative 6th to the negative 5th power, all over a to the negative third to the negative fifth power. So here we have an exponent to an exponent. Again, a power to a power. So again, we are going to multiply our exponents. So we have x, negative 6 times negative 5 is going to be positive 30. Y, negative 6 times negative 5, again, positive 30. All over a, negative 3 times negative 5 is positive 15. So that took care of the negative problem for us. So we got rid of the negatives by doing that. So that kind of killed two birds with one stone. And now our x's are all together, our y's are all together, our a's are all together. Everything's positive. We're good to go. This is our final answer. A to the 30th, y to the 30th, all over a to the 15th power. Example 3. 3 to the negative 4th, a to the 4th, b to the 9th, all over 4 to the negative 1, a to the negative 5, b to the negative 3rd power. Now here, I don't have to distribute any exponents or anything, but we just have a lot going on. So let's go ahead and make these negative exponents positive. So in order to make negative exponents positive, we are going to, where'd you go? We are going to flip them across the fraction bar. So meaning this 3 to the negative 4th power, to make it positive, it's going to go to the bottom. It's up top, it's going to flip down to the bottom. Likewise, this a to the negative 1st power, it's negative, it's going to flip to the top to become positive. This a to the negative 5th power, it's going to go to the top to become positive. This b to the negative 3rd power, it's going to go to the top to become positive. So by flipping all these things, they should all now have positive exponents. So starting off, this 4 to the negative 1 went to the top now, flipped to the top, and is now positive. This 3 to the negative 4th flipped to the bottom to become positive. This a to the 4th is already up top, so it's going to stay up top. This a is dealing with a. This a to the negative 5th is going to flip to the top to become positive. Well, now our b. So this b to the 9th is up top. Nothing's happening to it, so it's going to stay up top. And then this b to the negative 3rd, it's on the bottom. We're going to flip it to the top, so it becomes b to the positive 3rd power. So now we got rid of our negative exponent. So now let's kind of deal with simplifying. So up top we have 4 to the 1st power, which is just 4. We have, let's deal with these a's. So we have a to the 4 times a to the 5th. They're being multiplied together. These two a's are being multiplied together. So we are going to add our exponents. So a to the power of 4 plus 5. Same thing with our b's. B to the 9 times b cubed. We're multiplying those two terms together, so that means we're going to add our exponents. So b to the 9 plus 3. And then on the bottom we have 3 to the 4th. So my calculator, 3 to the 4th power, or 3 times 3 times 3 times 3, will give me positive 81. So that's the only thing left over on the bottom. All right, so going further, simplifying, looking at my 4 and my 81, there's nothing that 4 and 81 have in common, so I can't simplify that. So 4 is going to stay up top, 81 is going to stay on the bottom. A to the power of 4 plus 5 will give us a to the 9th. B to the power of 9 plus 3 is b to the 12th power. So looking at this, I can't simplify my coefficients. My a's are together, my b's are together, everything's positive. So we are good to go. That is our final answer. 4a to the 9th, b to the 12th, all over 81. Next example, 7x to the 9th y squared to the negative 1 power times 8x to the 4th y cubed. A lot going on here. Let's start by dealing with this negative. So that means that negative is saying that everything that is applied to everything inside our parentheses. So that means everything in the side of these parentheses is going to be flipped to the bottom because of that negative. So 7x to the ninth y squared got moved to the bottom, and then it's now to the positive 1 power because we flipped it, and that's what makes it positive. Now this 8x to the fourth y cubed, nothing's happening to it. There's no exponent or anything, so it's just going to stay up top. 7x to the ninth y squared is occurring one time to the first power, so we really don't need that first power. We can just write it as 8x to the fourth y cubed all over 7x to the ninth y squared. So now we can combine some like terms. So dealing with our 8 and 7, there's nothing that 8 and 7 have in common, so I really can't simplify anything with that. So 8's going to stay up top, 7's going to stay on the bottom. Oops. No. Okay, I'm sorry, let me rewrite this really quick. There you go. Okay, here we go. So, I'm sorry for that delay. So the 8's going to stay up top and the 7's going to stay on the bottom. So next we have x to the fourth divided by x to the ninth. We are dividing, so that means we are going to subtract our exponents. So it automatically goes to the top, so x to the 4 minus 9. And then same thing with our y's. This was y squared. So y cubed divided by y squared. So we're going to subtract our exponents, and they automatically go to the top. So that means we're left with 8 on top, 7 on the bottom, x to the 4 minus 9, which is negative 5, y to the 3 minus 2, which is positive 1. Now, we cannot have a negative exponent, so we have to make this x to the negative fifth power become positive. It's up top, so that means we're going to flip it to the bottom to become positive. So 8's up top, 7's on the bottom, x to the fifth is now being flipped to the bottom, and then y to the first power, which is just y, is going to stay up top. And that is our final answer. 8 times y all over 7x to the fifth power. Now, the last thing with this section is talking about scientific and standard notation. Because we use scientific and standard notation, we use exponents to help us write really big numbers or really small numbers in a different form. I'm sure you've seen a lot of this in your science classes because they deal with really, really big numbers and really, really small numbers. Our calculator screens can only hold so much, so they're super helpful, but we can only hold so much space on the screen. So that's when scientific notation comes into play. So standard notation is what we're used to seeing. So 1,200,000, 500,000, and then we have this really big number. So these are the same numbers just written in scientific notation. So scientific notation is where we're going to move the decimal. We move the decimal by showing 10 to some power. So that 10 to some power tells us we're going to move the decimal to that exponent amount. So in this case, I have 1.2 times 10 to the 6th power. So that's telling me I'm going to move the decimal 6 times. Then we have 5 times 10 to the 5th power. I'm going to move that decimal 5 times. 1 times 10 to the 22nd power. I'm going to move that decimal 22 times. And we're going to get these same exact numbers in standard notation. So notice that this first number is always between 1 and 10. So meaning we have to have 1 digit to the left of the decimal. So nothing more than 10. And then R is just a whole number, an integer. So writing a number in scientific notation, we're going to move the decimal until you have a single digit to the left of the decimal. And our exponent is going to be the number of places that we moved. Notice if you have a negative exponent, that means you're going to have a really, really small number. You're going to move the decimal. And then if you have a positive exponent, it's going to be a really, really big number. So write the following numbers in scientific notation. So from standard to scientific notation. First example, 730,000. So my decimal's at the very end. I'm going to move my decimal. Let me kind of zoom in so we can see it better. Moving my decimal 1, 2, 3, 4, 5 times. And notice I stop so that way it's 7.3. That's a number in between 1 and 10. I want to make it where there's only one digit, one number to the left of the decimal. So it's always times 10. It's always times 10. And then however many times I move the decimal. So in this case, I move my decimal 5 times. This is a really big number, so the exponent's going to be positive 5. And that's my final answer, 7.3 times 10 to the 5th power. So same way of writing the same numbers to different forms. Next example, 0.0000104. So I'm going to take my decimal and move it until there's one number to the left of the decimal. By the way, 0 doesn't count because if I can write this as just 0.000 and not write that 0 up front, so that's why we don't use 0. So I'm going to move that decimal until the 1 is in front of the decimal. So moving it 1, 2, 3, 4, 5, 6 times. 1, 2, 3, 4, 5, 6 times. So that'll leave me with 1.04. So I moved it until I got that one number to the left of the decimal. It's always times 10, and I move my decimal 6 times, so it's to the 6th power. Now, 0.0000104 is a really, really small number, so I'm going to have a negative exponent. So negative exponent because I have a small number. And that'll be my final answer, 1.04 times 10 to the negative 6th power. So again, because 0.000104 is between 0 and 1, it's a really small number, we are going to have a negative exponent. So now the same thing but opposite. So now we're going to go from scientific notation to standard notation. So our first example, 5.6 times 10 to the negative 7th power. So that means I'm going to take my 5.6 and I'm going to move my decimal 7 times. It's negative 7, so I know I'm going to have a really, really small number. So in order to make this a really, really small number, I'm going to move my decimal to the left 7 times. It's a small number, so move my decimal to the left. So moving it 1, 2, 3, 4, 5, 6, 7 times. There's my new decimal, and then filling in all of these gaps with zeros. So my final answer will be 0.000000056. Next one, 3.4 times 10 to the 8th power. Now this is a positive number, positive exponent. So I'm going to have a really big number. So in order to make a really big number, I'll move my decimal to the right. So 3.4, moving it to the right. 1, 2, 3, 4, 5, 6, 7, 8. So there's my decimal at the end, filling in all of my gaps with zeros. We'll have 3, 4. So putting in my commas, comma, comma. So 340 million will be my final answer. It looks like that decimal's there, but it's not. So I don't have to put this decimal at the very end because it's understood. All right, so that is great. So now dealing with stuff that's a little more our speed. Now we're going to compute with scientific notation. I want to multiply and divide really, really big numbers or really, really small numbers. Our calculators are great, but again, they only have a certain number of screen. So they only fit a certain number of places. So if you put in something really, really big, for example, like 5 times 10 to the 18th power, you'll get an error overflow message because our screen's not big enough to show that number. So that's why scientific notation is helpful, because we can still do stuff with these really big and really small numbers, but we have to put it in scientific notation. So perform the indicated operation, writing our answer in scientific notation. 5 times 10 to the 18th power times 2.9 10 to the negative 4th power. Now remember, this is just some really, really big number times another really, really small number. So there's just a number times a number. So, but here it's kind of like we're going to combine like terms. So combining our coefficients, our numbers out front. So 5 times 2.9. Oops. Which in our calculator, 5 times 2.9 will give us 14.5. And then we're going to do times, combining our places that we're going to move our decimal, our tenths, so to speak. So 10 to the 18th power times 10 to the negative 4th power. So notice we are multiplying two exponential expressions. So we did this earlier in this section. So we're multiplying. That means we are going to add our exponents. Parentheses around here. So 10 to the 18 plus negative 4, which is the same thing as saying 10 to the 18 minus 4, which is 10 to the 14th power. So I have 14.5 times 10 to the 14th power. But if you notice, I can only have one digit to the left of the decimal. This number has to be between 1 and 10. So it's not, it's bigger. So that means I have to move this decimal, and don't forget this part, everyone always does, 1 time to the left to make it 1.45. Times. Now 10 to the 14th power means that I would be moving it to make it a really big number, so moving it 14 times to the right. So if you notice, these are going in opposite directions. So that means I'm going to have to do it one more time in the end. So one more time than 14 is 15. So 1.45 times 10 to the 15th power. Let's do another one of those examples. This time it's the same exact concept, but we're going to be dividing. So 2.4 times 10 to the negative 9th, all over 4 times 10 to the 7th. Again, combining somewhat like terms. So doing 2.4 divided by 4 in our calculator will give us 0.6 times. Now doing our tens places in our 10 to the negative 9th divided by 10 to the 7th. Here we're dividing, so here we are going to subtract our exponents. They're like terms because they're both base 10. So subtracting those exponents, so 10 to the negative 9 minus 7, which will give us 10 to the negative 16th power. So 0.6 times 10 to the negative 16th power. Again, just like up here, 0.6 is not between 1 and 10. I need one digit to the left of the decimal. So that means I need to move that decimal one time, this time to the right. So if I have the negative 16th power, that means it's going to be a really, really small number. That means my decimal is going to be moving to the left 16 times. So again, these are opposite directions. So one's going to the left, one's going to the right. So that means in the end, I'm going to need to move it one more time. So I have 6 times 10, because I moved the decimal, so it'd be like 6.0, times 10 to the negative. The negative just tells me left or right. But 16, I need to move it one more time. So 1 more than 16 is 17. So 6 times 10 to the negative 17 power is my answer. Now, I always get the question of, well, what if it's moving the same direction? So what if, total another example, what if I had 0.6 times 10 to the positive 16 power? Again, I would have to move that decimal one time to the right. But this time, 16 means it's going to be a positive number, which means it's already going to the right. So instead of moving it 16 times, already moving it one time in the right direction already. So that means I'd have to move it one less time in the end. So here I'd have 6 times 10, and then one less time than 16 would be 15. So moral of the story, if it's going to be same direction, let me write this down here. So same direction. So 1 less time. And then up here I had opposite directions. So moving it 1 more time. And then we just dealt with a lot of stuff. So I thought it might be helpful to put it all together in one sheet as like a little handout, a little summary of everything. So we talked about multiplying exponents. Here we would add our multiplying exponential expressions. We would add our exponents. Dividing exponential expressions, we're going to subtract our exponents. Raising a power to a power, we were going to multiply those exponents. Remember, if it's a negative, we're going to flip it down to the bottom. This, I just noticed, this should be a negative 12. X to the negative 12. Oops, why is my calibration? All right, so x to the negative 12, so that's what makes it move to the bottom. And make it 1 over x to the 12th. 0 exponent, so anything raised to the 0 power is going to be 1. So for example, 2 to the 0 power is 1. And then again, the negative exponents, flip it across the fraction bar. Here's a little extra about scientific and standard notation. Make sure there's only 1 digit to the left of the decimal. Negative exponents are for really small numbers. Positive exponents are for really big numbers. And always make sure your final answer is a number, our decimal, and then whatever is left over in the back. So that is 2.5 notes. As always, if you have any questions, please reach out to me or our tutor, and you should be good to go. Thank you.